has been trying to understand when to plant the crops and actually harvest them. And 2,200 years ago, it's estimated that they built this mechanism, the Antikythera, found in the bottom of the Mediterranean. And it was a mechanism that has several gears that predict the motion of the planets, even the next Olympiad. And what is nice about it is that it's a mechanical device that simulates the mechanical motion of things, right? So using mechanical technology, we're already thinking as a civilization to simulate classical motion. But then, of course, computers came in, and there is this beautiful book by Peter Galison, who is a professor of physics and history of science at Harvard, which is about the birth of the field of computer simulation, right? So when the digital revolution happened, and it is during the Second World War that a lot of this action happened, trying to predict the scattering of neutrons in the reactors of nuclear reactors, that people started thinking about more deeply about simulation. And Peter talks about all the historical components of actually making these mongrel fields that combine different aspects from different subfields or disciplines. And one of them is, of course, computational science. And he says something beautiful in the book. He says that without computer simulation, the culture of the late 20th century, of course, this 21st century as well, will not be merely inconvenience. It wouldn't exist, okay? Machines are inseparable from the virtual counterparts, all around to simulations. He means, for example, that a computer chip was simulated by another computer chip. We'll come back to that later. And basically, a lot of the technology that you use every day, like cars, was computer simulated. So now simulation became part of our reality, and it's kind of like a Russian doll of success of humanity, right? So it is where this is James's great grandparent or something like that, advisor. He's the advisor of the advisor of the advisor of my postdoctoral advisor, something like that, Samuel Boyce. Okay. He, in 1955, did the first digital simulation of a molecule on the EDSAC computer in Cambridge. Okay. And his student, John Popple, that won the Nobel Prize together with Nick Handy and Isaiah Chavez, wrote about this beautiful conference he gave in 1955's Molecular Quantum Mechanics Conference. He came in with the first computer program that simulated the electronic structure of molecules. And it was a printout that he unfolded on the table. And he said, well, if one question enters in one side of the table, there's another answer that comes out on the other. And the audience was kind of, shaken by this, according to the three students of him. But it's very prescient, and I like to do close readings. I guess that happens when you're married to somebody that did English literature in her scholarly work. If you do the close reading more than about this, then it's kind of super interesting, because you might even think about this as a kind of premonition of Google or this type of other computer systems that you ask a question and you get an answer. And part of my research in terms of AI and chemistry, which I'm not going to talk to you about today, actually is inspired by this kind of vision of Samuel Boyce. Okay. So anyway, here is another influential figure. This is Richard Feynman in an Apple ad. His paper simulated physics with computers, published in the perhaps modest journal, the International Journal of Theoretical Physics. Is his most cited paper, okay? More than his QED papers and his other fancy papers, the paper where he's talking about the fact that maybe for simulating quantum mechanics, you need a quantum device, and also gives kind of the premonition of quantum computing. It's a fantastic read. I recommend everybody to read it. And this shows you how well, Apple makes advertisements. It's a beautiful early advertisement showing this beautiful picture of Richard Feynman. And I would like to say that during the pandemic, Apple's advertisement has gone downhill. Look at a current ad of Apple. It looks pretty ugly compared to that beautiful picture of Feynman. So hopefully Apple goes back to those kind of more inspiring advertisements. But anyway, so kind of like the way of the Mandalorian, the quantum simulation way involves the following. You take your mathematical model, and as James told you, like I'm a chemist, so for me, I'm very excited about this molecule. And whenever I speak in an auditorium, I ask the physicists if they know what this molecule is. And I remember being in the Harvard physics department and ask people, can you please tell me what is this molecule? And then the physicists, almost nobody could tell me what it was. And turns out it's just acetone, okay? But it's funny to see them nervous, okay? So this is just acetone. And I take acetone and I just map it to its model, for example, the time-independent Schrodinger equation, simplest equation that we learned very, very early on in undergraduate, or a time-dependent Schrodinger equation, or if you want to have the relativistic model, that is fine. A mathematical model that represents such a molecule, maybe the molecule with its environment. Doesn't matter. Really what the whole thing is all about is, as Feynman proposed, rather than using a classical information processor like the one that I showed you of Samuel F. Boyce, change the paradigm, right? So we're really talking about 1955 to 1982, where the proposal happened, to a seminal paper, actually from a mentor, collaborator, and friend of Lorenza, Professor Seth Lloyd at MIT, who proposed a paper in 1996 that kind of formalizes the whole thing about quantum simulation, like shows that for local Hamiltonians, quantum simulation is efficient. So that allows us to then extract a polynomial amount of information out of the system. Okay, another topic that both James and Lorenzo have worked on a lot, but the topic of what can we measure out of quantum computers. And turns out that we can measure a polynomial amount of information out of them. And in this case, for example, we could take out its energy or its dipole moment, or we could take out a subset of information, right? So if you want to read out all the information of a quantum mechanical system, it doesn't scale very well because the wave function of the system scales exponentially with the number of quantum resources that you add. But it is very seldom or almost never that you will want to really know everything about a system. It's too much information. So you just want to know something like its energy or its dipole moment. So this is kind of like the main idea behind the rest of this talk, but I'm going to try to go into more detail. So now, because we're talking about all these generations, James talked about his student Kanav. He was my student as well. Now I want to go to my advisor, whose advisor was a guy that wrote about Bosch, right? So Martin Head Gordon, a student of John Popple. So what Martin wrote in this paper in 2008 is just a simple estimate of the polynomial methods that you need to solve the Schrodinger equation, density functional theory you might have heard about, second order perturbation theory, coupled cluster theory. And I actually believe that this plot was generated by James himself when he was one of my graduate students, actually, if I remember correctly, James. We made a version of this plot for a museum in Japan, if James remembers. But anyway, this is the original paper. This is basically the same data from his paper, which extrapolates extremely well now to 2021, okay? So it is incredible how this is just so simple, right? You just imagine Moore's law keeps growing, and supercomputers kind of keep growing at the same rate. So this kind of predicts, what type of molecule can you do with these methods? And notice how this method scales as between the 6th and the 7th power of the molecular size. It's still at a few tens of atoms. And this is kind of the gold standard. We'll come back to it. It's called coupled cluster. This is the exact, sometimes called exact diagonalization or full configuration interaction in chemistry. You notice that because the resources of the classical computer are growing exponentially with Moore's law, they don't really catch up to this factorial growth of all the number of configurations that you need to simulate a molecule exactly, right? So this is actually a slot, a line that again James and I put in the plot long time ago that says, imagine, and this is the time when we started working together. Imagine that there was a polynomial growth in the number of quantum resources available to you. And you could, in principle, have a polynomially scaling algorithm, as Feynman and Seth Lloyd had said earlier on. And then I followed on in 2005 on this idea. Then, in principle, one day we will cross the exact line, because this will be a line that grows polynomially with system size. How steep it is, we'll come back to it as well. But then eventually you will cross these methods and then basically retire them. because unlike the classical computer, this line is exact within a basis. So it will be the exact simulation of a molecule, not the approximate. So I do believe that's disruptive. The same way the digital camera was disruptive, making camera picture taking ubiquitous. This is going to be the same thing because you're going to have now exact simulation broadly available. There was a topic called supremacy. I hate the name, obviously, it has political connotations, and in a liberal arts college, kind of sucks that we have to use that word, but that's the way a former postdoc of my lab, actually, Sergio Boixo, named this idea that a quantum computer will be better than a classical computer, okay? At a particular any task. And turns out, as we will talk later in this lecture, it has happened. And there's arguments if, people now have, outperformed the original experiments by Google that Sergio led with classical computers or not. And to be honest, to preempt a question that anybody will ask, it doesn't really matter if supremacy has been achieved or not, because if a classical computer can supersede a quantum one, you can just make quantum computers slightly larger and again supersede the classical one. What it means is that we're at the supremacy border, and like quantum computers and classical computers in certain tasks are basically duking it out, which is extremely impressive. But ultimately, I co-founded a company called Zapata Computing, actually, that also James helps co-advise. And Zapata Computing has a very practical aspect for this. I mean, the way Zapata talks to its customers, and these are big large companies, about quantum computing is that doesn't count. What counts is when you take any process that you have in your company and you replace that process by a quantum computation, no matter what reason, power, heuristic reasons, etc. That hasn't happened, by the way. We don't know of any company, a real business, that replaced part of the workflows by anything done in a quantum computer. And we're very honest about it at Zapata, my company, and also my research group. But I believe it's coming. And this is the reason why also the investors in Zapata and many people are very interested in this technology. And so we'll see why. I mean, it's growing really quickly. But the reasons that this might enter the workplace might not be very computationally formal. They might be more heuristic, as I told you. Like, it's faster, but is it more efficient? We don't know. Is it, etc. So, but our working definition is that advantage will be that, okay? So a practical task done by a quantum computer in the real world for any reason. Okay, so this is a colloquium. So I have to kind of tell you what is a quantum computer, right? So imagine that you have classical information is current or no current, voltage or no voltage, flip or no flip, up and down, etc. Just two binary numbers usually. You could also have classical information in other bases, but you might just 0 and 1. The quantum version, if you remember your quantum mechanics, you can allow for superpositions between quantum states, and each quantum state can have an amplitude that is a complex number. If you normalize the wave function and remove a global phase for a two-level system, you can always write down the wave function of a two-level system as a dot in a sphere. Okay, the normalization will be the size of the sphere, which by rules of quantum mechanics, basically the size of this vector has to be 1. And then the vector could be in two classical states, which will be your preferred measurement basis. In this case, say it's z. So you can imagine that taking the z axis of this block sphere will be the 0 and 1 poles will represent your classical information. And any place in between will be this interesting state of superposition, right? Which in some sense is the system rotated to another basis. And note that you have also the interesting equator, which is basically complex numbers. Like the imaginary part will go along there, right? So you have the x, y, and z operators that will be able to rotate. The rotation operators will allow you to rotate along those 3 different axes. And what is a quantum computer is a collection of controllable versions of these qubits. So anything that can produce to you a controllable two-level system that can be entangled with its neighbors. And usually entanglement is very easy to achieve, because if you have a two-level system and it has some physical mechanism of interacting with its environment, if you can control it, it can be sitting next to a neighbor and the neighbor will also interact with it. And now it's just a question if you can turn it on and off and make sure these two guys talk to each other in a controllable way. And the most schizophrenic thing about a quantum computer is that you need to make sure that it is as isolated from the environment as possible, at the same time that it is controllable, which means being open to the environment. And this is where I like to really refer to my colleagues' work. I think this is where Lorenza has made, among many other things, like fantastic, seminal contributions to the field, because she's been thinking a lot about this issue of noise and control and understanding how to really think about these qubits in this context, okay, over her career. And it is that kind of those seminal contributions that matter. And one of them, of course, that is basically is the field, okay, which again she has contributed a lot, and also, for example, the seminal work of Peter Shor of error correction, right? And in error correction, you imagine a possibility where all your qubits information is perfectly preserved, okay? And this is the result, I think, that really allows for us to even talk about quantum computers, for us to even talk about scaling, for us to even talk about the future of this entire field. We had to rely on these theorems of error correction that tells us that we're going to get to machines that are going to have the ability to reproduce errors. And error correction shouldn't be scary to anybody. I mean, there are very simple ways of doing it, and classical computers have error correction codes, even though sometimes they keep crashing, right? So now, this is a slide that I like to use because I used since I was a postdoc, just to give you graphically what really happens in a quantum algorithm in a simplified way. You can see here, I'm trying to represent those complex amplitudes over a set of 3 qubits, which means 8 quantum states. A classical algorithm will start with a particular classical state, for example, polarizing all your spins to the top. And then if you were to send a pulse to all your spins or all your qubits, then all of them, for example, in the equator after a pulse, then they will be in a superposition of all qubits with respect to that computational basis. Again, the only thing you did is rotated all of them along this new basis, right? But then after certain type of operations, there could be single or 2 qubit or even multi-qubit operations that entangle them. You might want to refocus your amplitude after you did some sort of computation around the answers that you're seeking. And this is kind of like a needle in a haystack, because if you keep adding qubits, the number of available states goes to 2 to the n, whereas you usually want to get just one number, okay, which is 1 over 2 to the n kind of concentration of probability, right, that you need to actually do in your quantum algorithm to get something meaningful. So in a very, very vague way, this is how we think about this. So now, again, you have to think about the operations that are done in these systems, and I already told you about that pulse. We call it Hadamard gate, that will allow you to get to that equator, and that's what I'm showing you here. It will be represented by this matrix over the state vector of the qubits. These particular rotations will allow you again to rotate along the different axes of the block sphere. And this is just an example of a potential 2-qubit gate, the so-called control NOT gate. Depending on the amplitudes on this qubit, then the other qubit will flip sign, and this could be also done in superposition. And finally, you're able to see a picture of a quantum algorithm. You will see here, say, 3 qubits carrying out the quantum Fourier transform, applying single and 2-qubit gates. That again, I'm not defining here what is an S gate and a T gate, but gives you an idea of the type of operations that you will need to do, for example, for doing a Fourier transform on a quantum computer. So now we can think about quantum resources. So what does it mean? So first of all, these operations that are kind of like music are literally control pulses sent to these qubits that can be abstracted as these gates. One of these gates could require more than one pulse, or a composite pulses or things like that. But the point is that these gates can be then concatenated into a big, large unitary operation that we like to call a quantum algorithm, whose depth will be the number of subsequent set of gates that you apply. Again, these are abstractions. And then the width will be the number of qubits. And with an extra parameter involved, IBM created this idea of the quantum volume, which is an idea. That parameter, by the way, is related to fidelity of these qubits. It gives you an idea of how powerful is a quantum computer. And if you don't think about a quantum computer that is error corrected at the moment, the coherence will eventually destroy it. And you want to think about in terms of its volume, or in this case, simplification, the area, how many gates and how many qubits you can apply those gates to before your information is destroyed. And then you need to have enough variability to be able to cover the possible states that you're going to be using for your computation. And to enable universal computation, it suffices to have the three Pauli matrices X, Y, Z. Of course, I is another Pauli matrix that is just, obviated here, but of course completes the group. And then completes this. And then you can imagine having basically the generators. This will be the generators of these rotations that I told you about before. So now this is where there is a very important name for your department here, Professor James D. Whitfield, which basically was the student that followed up the work I did as a postdoc with Martin, with Tony Dutoy and Peter Loeb. And I keep seeing that typo since I've been giving the seminars my entire last few months, so I want to fix it in front of you. So now I can be happy. So this is a figure from the original paper. This tells us how to implement the original proposal of Seth Lloyd for molecules. So the way you want to think about this algorithm, and I'm going to read your quantum algorithm right now. And I know that I just taught you this in a few slides, but bear with me. This is a register, a multi-set of qubits that will represent a molecular wave function. This U is its unitary time evolution operator. If you have taken quantum mechanics, you know that you can evolve a quantum system by applying this operator, e to the minus I Hamiltonian t. And then you are applying that operator longer and longer in time. And these are basically successive powers of 2 of longer in time. And why is that? Because you're entangling successive powers of 2 of that power in time with a qubit that was placed in that superposition that we talked about. So what is very interesting about is that these successive powers of 2 are there for a reason. They are there for a binary expansion of the phase, a binary expansion of this rotating phase that will be obtained if you act with this operator on an eigenstate. So what basically is going on is that that phase will rotate at the speed of at a speed proportional to the energy of the system. And therefore, if you have the ground state, say here, what you're doing here is in the time domain, entangling its time evolution, expressing it in a binary format. This is the reason why these 2, 4, and 8 are here. Doing an inverse quantum Fourier transform, and then you go from the time domain to the frequency domain, and then you read a peak. That frequency is the speed of oscillation of the system, and that speed of oscillation will be related to its energy. So it's kind of like a metrology question really here. And if you use that algorithm, you can look at molecules and see very interesting things, right? So what we did, basically, we say, okay, first thing was, okay, this can be applied to molecules. But second is, okay, let's work out all the details. And this is what this now seminal paper by James did. It won actually the prize of the journal that year. I love to brag about Professor Whitfield here. But basically, what James did is really worked out the first real full cost of this algorithm. And turns out the cost is very astronomical. If you don't do many tricks, we found out, thanks to James's work, the work is astronomical, but still polynomially scaling, which means that it's more efficient than full configuration interaction or exact ionization. And also we have the interesting property that as you grow the size of the molecule linearly, you will only need a linear number of qubits, which means that molecules that are very, very intractable, impossible to do in classical computers, will be eventually available in the domains of, say, 100 qubits. So I've been mentioning this error correction situation. And of course, eventually, when we have error correction, I predict, and maybe I'm wrong, but this is my bet, that the first person that can do an error-corrected qubit, basically a phase of matter that is going to be new, right? We have a quantum superposition or entangled state that could exist if it's more than 1 qubit, that could exist forever. Even if the only thing you are doing is a quantum memory that is perfect and is error-corrected, I argue that's kind of like a Nobel Prize winning achievement, because you will have the first kind of very non-trivial thing using quantum mechanics, right? You are fighting the coherence forever, right? So I would imagine that if I was such a person, I would just let the computer run for 2 years. I have a quantum state going for 2 years, even if it's not doing computation. Just pause and think about such an experiment, how amazing that would be. So that's going to happen, hopefully, within a few years, I think, I don't know, a decade, I have no idea exactly when. I predict that my own experience, from what I'm seeing, I think this is going to be possible to have enough number of qubits and enough control to be able to at least have 1 qubit in the fully error-corrected regime And that's going to be just an amazing thing for the field. But right now, we're not in that space. We're in a very weird space where we have these qubits with enough quantum coherence to achieve this so-called quantum supremacy. So it's non-trivial, right? Simulating even their dynamics is complicated. But nobody has shown that they are useful for anything computationally meaningful for industry. So we have algorithms and hints and a lot of even results that tells us that it is going to be possible to do interesting things with these NISQ machines. The question is when exactly. And that's in a matter of years, I think. So that's the exciting part of the field. And therefore, notice how this paper, I mean, this term was coined by John Preskill, and this is a plot from Rigetti and so on, talks about quantum chemistry, the application that we kind of started working on with James, optimization and machine learning and some of the applications. So now the field is moving so quickly that I ended up participating in 3 reviews over the last 3 years on it. This one came from a workshop that we did in NSF. Actually, James was also a participant on that workshop. Quantum chemistry in the age of quantum computing. We kind of wrote a chemical reviews, which is equivalent of the unrev kind of thing. Rep mod fit, sorry, for chemistry. And it's a huge kind of compilation of all the papers that were available for quantum computing for chemistry in 2019. Then I was invited to participate in this review that was written more by physicists in Rep mod phys. More or less similar topic, but different tutorial style and etc. You can read all of them. And finally, we just put in the archive this monster in collaboration with the group of Leong Chuan Kwek in Singapore. And what it's amazing about this review, we wrote it because we just couldn't keep up with the field, as I'll show you. We couldn't keep up with all the applications that people were proposing for NISQ. So I told my team, why don't we write a review? Like, let's just catch up. It's incredible. Okay. So now I want to show you more or less what are those algorithms for these near-term quantum computers. I'm going to tell you about them for chemistry, and also I will be telling you about, in general, these algorithms for NISQ for the remainder of this talk. So this is the half an hour mark where people have to breathe a little bit. Actually, I'm leaving the introductory piece, and now we're going to get a little bit more technical and then come out. Okay, so we were also very lucky because we produced the first NISQ algorithm together with Eddie Farhi the same year. We put this in the archive in 2012. Sorry, 2013 maybe. And what the paper was called, it's called the Variational Eigensolver. I'll spend time explaining to you what it is. But what that algorithm is doing is trying to optimize the energy of a system for a near-term quantum computer. Okay, at the time, we already were doing experiments with many people in near-term quantum computers that were very small. And we noticed that those experiments, the only thing we could do was that, basically. Eddie Farhi came up with an optimization algorithm. And then since then, we've been working, this is just work from my group. This is already published. I should change this as well. We worked on, basically generative models for machine learning applications. But today, I'm just going to tell you about just the Eigensolver pretty much. But these ones are all taking the same thing that happens in machine learning. That's what machine learning is connected to this. You take an objective function, it's called loss function sometimes in the field, okay? And you minimize or maximize it. You're trying to find a circuit that is tuned to minimize or maximize such a thing, like minimizing an energy, maximizing a cut size in an optimization problem. This is a beautiful kind of, one of the students of Lorenza worked on this project here. His name is Peter Johnson. And Peter, coming from Lorenza's fantastic quantum information background, did teach me a lot about what does it mean to compress information through quantum channels. And this quantum autoencoder is nothing more than kind of Schumacher's quantum compression ideas, but applied to a near-term quantum algorithm, how to compress quantum information in the context of machine learning. So that tells you about the connections between fundamental quantum information theory and application algorithms. They are connected all the time. So you can work in fundamental theorems and they will have direct impact in these applications I'm telling you about. So that's something to keep in mind, okay? So when you're doing your PhD, especially for the students in the room, you might be doing something very theoretical, but it's going to have deep implications. So this is an example, right? just the algorithms for many body physics that we were able to collect for the quantum computers. Again, the work of James is all over this as well, in a lot of these papers as well. So I just want to say that. So here are variational algorithms. These are imaginary time evolutions, excited state algorithms, simulation of dynamics, simulation of open quantum system, state preparations, our autoencoder and other autoencoders that came out as well, etc. Okay, this is just quantum simulation. Again, I'm just trying to show you this list of results because notice the years. Most of them say 2020. That's why we wrote that review. It's just like insane. Look at this. These are interesting applications in machine learning, quantum Boltzmann machines, quantum kernel methods, reinforcement learning, okay? Applications in quantum optimization following the work of Eddie Farhi. Again, notice how most of the years are 2019 and 2020. Huge explosion. Other applications that I like to mention, more and more, this is what's going to happen, I think, the expansion of these ideas to linear algebra and all the things that you can do with linear algebra will become more important. And I know that there is always this dark mermaid that is sitting on an island that takes theoretical physicists and takes them to finance. So quantum finance is becoming more and more popular. And I think this is going to be a huge field. Okay, so all of you that want to make money and go to Wall Street and help these rich hedge fund managers build quantum computers to predict the market, that's going to start happening. And finally, there's other applications here in fields that I've been addressing, like metrology. And again, this is Peter Johnson at Dartmouth not surprisingly, worked with me on an error correction algorithm called quantum variational error corrector. You can see where his lineage comes from. Quantum optimal control, inequalities, etc. Beautiful, right? So it's just beautiful where we are. So now let me tell you one algorithm, otherwise you're like,
so Alán, if I can pause you for a second.
Yeah.
We have a question in the chat.
Please.
This is from our incoming postdoc, Joshua Heath. And it says, is there a known quantum algorithm which can extract the frequency dependence of the imaginary component of the electronic self-energy for a given strongly correlated system?
I know where you're going. You're a condensed matter folk.
Yep.
And you know, let me tell you something, Joshua. I don't know exactly if there is an algorithm for extracting that. Let me explain what I mean when I say. Sometimes say you're thinking in self-energy terms and these perturbation theory type expansions and so on, and you want to map them to a quantum computer, and you go down that path. And actually, James and I have gone down that path together when he was my graduate student. We're trying to do density functional theory in a quantum computer and things like that. You start doing any method like that in a quantum computer, and you realize that it's better to simulate things exactly. Okay, so how about if I replace your question? If you give me a physical observable that corresponds to that, but you just remember that you just told me something about the self-energy, which is kind of like a mathematical object. Rephrase it to, you know, an observable that is of the real physical system, and my answer is yes. And actually, my argument is in quantum computers, you probably don't want to think that way. You probably want to think in terms of the real observables. And I hope this answers the question. Happy to go into Q&A later or in the quantum T and discuss more about that. But that specific, go to my review, maybe Google if there's something about how to do this exact calculation. I don't think that would be the right way of attacking it, but maybe I'm wrong, okay? I love to be proved wrong. And if I'm wrong, just ask me for a tequila shot in the next physics meeting. So now, thank you, James. And feel free to keep asking questions, people. So what is a variational algorithm? So let's go a little bit poetic and say you go to your Instagram reels and you're just paging through the reels, and then you see somebody playing a guitar and tuning a guitar, right? So a quantum algorithm like this, you can think about it as tuning a guitar. What you're trying to do is you take a circuit that has all these parameters. There will be the rotation angles. Remember those angles I told you about of 1 and 2 qubit gates? And there will be perhaps the degree of entanglement with 2 different qubits. You know, maybe you have a controlled Z rotation. And those depend on a set of parameters. They are denoted as theta here, that is polynomially scaling with the size of the system. Those are the knobs of the quantum circuit. The quantum circuit is your guitar, and as you tune the guitar, what you're really doing is you take the quantum circuit that is used only to prepare a quantum state, and then you measure in the state. In particularly, you measure a series of operators that correspond to the Hamiltonian or energy function of the system. That was our idea of the variational eigensolver. Then the advantage of doing this is that then all the classical processing goes outside of the quantum computer, and the only thing the quantum computer is a state preparation and measurement device. Okay, and what I mean by classical operations will be adding the terms, averaging, and then optimizing with a classical optimizer. What is the next set of parameters to try? So these algorithms really require a lot of measurement and a lot of averaging, but really they are really tuning a guitar. Now, for those of you that know machine learning, see the connection. What is machine learning? Machine learning is pretty much the same thing. If you think about, in particular, deep learning, but even other models, but just think about the deep learning models. You have a bunch of neurons with parameters that are tuned by a technique called backpropagation, which it's fine. Whatever the technique is, you're actually changing those parameters to fit a data set. And that's the connection between variational algorithms and machine learning. But going back to electronic structure, this variational eigensolver has many, many good properties. So even in our 2014 paper, it's kind of vintage now. You see here our mention of the word QPU that is now commonplace. QPU means, okay, the quantum computer really is just like a GPU, like an auxiliary processor that you're going to ship this task of preparing and measuring a quantum state. But notice that you could, in principle, have a room full of quantum computers, which I argue is going to be one of the future things that is going to happen. People are going to realize that it's actually valuable to have a room with 10,000 30-qubit quantum computers or something like that. It will still have some advantage. Maybe they have up to be 100 or 200 qubits, whatever the size they are, right? These quantum computers could calculate different terms of Hamiltonian in parallel. Then you use a classical adder and classical decisions to come up with the parameters of the next circuit. So it's as simple as that. So of course now, things have advanced a lot. Okay, so under the hood, you take the many body generators. And again, this is what I want to brag. I think about your own faculty, one of the leaders in the world, if not the leader in the world of understanding how to do these mappings is actually James. James has done seminal work on thinking about how you take a many-body Hamiltonian and you map the Hamiltonian, which is written in terms of fermions, into spin 1/2 particles. Those mappings are not unique. There are pros and cons for them, and one of the experts in the world is here. And the point is, a lot of that has been coded in packages such as OpenFermion. So the point is that there's a lot of computational machinery that takes you from the generators of the Hamiltonian all the way down to variational minimization. And what are the things that are happening here? Okay, the fast-moving algorithm land is crazy. People are thinking about excited states, as you saw in the plots I told you before. Optimization methods, ansatz adaptive methods, you name it. Tons of people at companies and academia. Examples of developments that I think are amazing. So if you think about the naive scaling of the number of measurements required to simulate a Hamiltonian, it will be n to the 4, and that doesn't even count the statistics for each one of those terms. So what is very interesting about this is that over the years, including former students of mine like Ryan Babush, or our colleague in Toronto, Artur Ismailov, many groups have started working on reductions in the cost of the number of measurements, and the scaling is now into the 1/4. So a lot of this algorithmic squeezing of the line is going to happen in the classical pre-processing and post-processing. And the way this has been done is by really thinking about the algebra of these operators and how many subsequent measurements can you do, how can you group the measurements, how to really think about the measurements in terms of group theory. Again, the use of theoretical tools to actually improve very practical algorithms. So now, James knows this story because when James joined my group, and I think this is a true story, James, the first package I gave him to work on is a code I did as a postdoc that we call Tequila. It was called Tony's Quantum Information Library with Alán. That was the title of the code, okay? And when we regrow, we, of course, didn't use Tequila anymore. Many years later, we wrote this simulator that is very high level for chemistry and variational algorithms in quantum computers. And we had to pick a name, and I said, let's name it Tequila again. So this is not the same Tequila, but you can tell that I'm a Mexican and I have to just put the stamp. But basically, what is so cool about Tequila, and I invite everybody to use it, it's an open source package, is that you can write your mathematical problem in the Blackboard like this. And this is the actual Python code that you need to do to evaluate and execute. And Tequila stands on top of all the packages from all these large companies, JAX, which is the automatic differentiation package, OpenFermion, the quantum chemistry packages, and it's a glue package that is done at a very high level. And what is very nice about it is that it uses this JAX package for automatic differentiation, which allows us to calculate the gradients of these objects for optimization purposes. What is also very nice is that literally you can calculate the benzene molecule, select it, the symmetry of its orbitals, obtain its amplitude, etc., all at a very high level. And this is really the work of my student James Sumner Alperin, and postdoc Jacob Kotman, of course, leading a larger team. But it's a beautiful package. I invite you to look at it. So something that we did with Tequila, and you will see that many of our papers came out in 2020, 2021, thanks to the fact that Tequila now you can write a small script, and that's a paper. Okay, so now I really recommend you, if you want to enter this field, you can just start coding in Tequila, and it will be much, much easier. But let me give you an example of how the thinking has gone. Like if you want to make a quantum computer do chemistry in a new way, what you might want to do is say, well, I'm going to take my traditional way of solving the problem, which is picking a basis set and then carrying out a calculation in that fixed basis set and just calculate a mean field correlation. This will be kind of what we will do in a classical computer because it's so cheap and efficient that you build that cheap model and then you build the correlation on top of it. But in a quantum computer, the quantum computer is so expensive, the qubits are so valuable, that maybe your best approach will be to do a very, very expensive basis that is done by multi-resolution analysis in a code called Madness. Then use a surrogate correlated model, for example, a second-order perturbation theory, to get the so-called pair natural orbitals, the best correlated single particle objects you can ever find, because the basis is in a grid and also is built with correlation in mind. And after that, in both cases, you truncate which orbitals you're going to use. But now you build a Hamiltonian and do the variational algorithm the same way. So notice that what we did is we detoured in the classical computing side, but at the end of the day, when we get to the quantum, we can use any of the other methods that several other groups have been using for the variational eigensolver. And that allows us to get these potential energy surfaces, which is the energy as a function of distance of a molecule, and extrapolate to an infinite basis set size. So basically trying to think about what would be the exact solution and see our costs using this technology versus using the traditional Gaussian basis sets. And in some cases, we get a factor of 2 to a factor of 10 in speed up. It's not really speed up, but reduction in resources, which tells you that a lot of the thinking nowadays, and just want to tell you what's going on, is thinking about the classical side of the coin here as well. Okay, so I'm going to look at my time and notice that I have very few minutes left. So I'm going to skip a lot of technology. Okay, really a lot of technology, and maybe tell you two more stories. Okay, do you guys remember the idea of supremacy, right? So I'm going to get into it with work that we've done with my former student Nico Sawaya and Giangiacomo Borrecci, and also Tiha Kiao in my lab, and others, of course, here listed. So it's the idea of a new application for quantum computers. Look at this. So this is the supremacy experiment from Google, right? A classical computer cannot simulate it. If you don't believe me, well, there's even a probably more impressive experiment coming out from China, from the group of Jiawei Pan. It's an extremely large quantum optics experiment that is also unsimulatable, as far as I know. Which basically means the following. Look at this plot. Remember Moore's law? Well, this is the number of transmons in the qubits that have been reported recently, okay, in different systems. So this is a log linear plot. So to me, it looks pretty Moore lawish. So the qubits are becoming more and more. Of course, they are not error corrected, but still. And this is the quantum resources that grow to simulate it. So supremacy happened when there is a big gap between the size of the supercomputers and the size of the number of qubits. And this is basically exacerbated every year, every second, okay? So we said maybe an application of quantum computers is to simulate themselves like a Russian doll, okay? Because if you want to design a quantum computer, you will need a simulator. Do you guys remember the talk, the quote of Peter Gallison? So I inspire myself a lot when I read things. And in that particular case, he was saying the world cannot be inconvenienced. It wouldn't exist if it's not simulated by other computers. And computer chips are simulated by computer chips. If you really want to understand the noise parameters or you want to understand the dynamics of a complex quantum system that is a superconducting qubit, for example, you need to simulate it. So it turns out we did a lot of work that I'm gonna summarize in one slide, basically, to show that you can do variational Eigensolver, quantum dynamics, all the algorithms I told you about very briefly, with simulation of 16 levels, 4 qubits per qubit. So in the case of superconductors, you only lose 4 data qubits per qubit, and you can simulate the superconductor basically exact, okay? Which basically means that if you want to simulate a quantum computer with another quantum computer, we believe the quantum application type of limit, where you might be able to simulate better using a classical than a quantum, is coming up in the next couple of years, according to this plot. Who knows? Okay, you still need the quantum computer to be able to have enough coherence to simulate larger and larger blocks. So it might come later in the future. We might not have enough coherence to do this, but still, future quantum computers simulate the design of existing quantum computers. This is kind of the new application, and we call it quantum computer-aided design. Again, it's in all these papers that appeared last year. So different aspects of it. So that's kind of like the new secret project I had in my lab going on for a couple of years. And I'm going to skip everything about it because I want to have time for questions. So sorry about that. Now let me show you a little bit of history to end this talk and then have time for questions. This is 2016 experiment, so vintage. It's the quantum 9-qubit chip that Google had at the time in the refrigerator. We used 2 qubits of it to do the variational Eigensolver, okay, in 2 qubits only, for the hydrogen molecule in the minimal basis. And this is the red plot is the variational Eigensolver, and these blue dots is the original phase estimation algorithm that James and I worked on so many times. Notice that without error correction, phase estimation is a little bit hopeless because it requires more gates and therefore has more noise. But this is an example of how results in a quantum computer were 5 years ago. Let's fast forward really quickly. 2 years later, we published in PRX with a group of Rainer-Blatt a 4-qubit experiment for the potential energy surface of the lithium hydride molecule. You can see here the variational algorithm in action, the experimental results from the ion trap quantum computer. Then a year later, or around the same time, beautiful paper, 7 qubits by Jay Gambetta and team at IBM. They simulated in that 7-qubit computer the beryllium hydride molecule. At the time was the largest simulation, and you can see here its potential energy surface, and of course the errors. You can even see shades of the excited state here, telling you errors about the state preparation, and so there's a lot of things that you can improve on this algorithm. But you can see how they really are connecting the qubits, kind of in a similar way as the how do you say that? As the qubits in this layout. So one of my favorite papers, taking pictures of molecular orbitals and drawing them literally on top of a physical device. Nothing more similar to the Antikythera that you saw at the beginning of this talk. It's the same kind of philosophy, right? Now, let's fast forward to last year. This is Google's experiment. Hartree Fock on a quantum computer, 12 qubits in a hydrogen chain. People criticize this because it's preparation of a mean field state. I'd say it's still a tour de force of what you can do now in a quantum computer. They took this plaquette and they only were able to do 12 qubits with this circuit depth, and then measure the energy with a very, very, very small energy error for this particular simple wave function. Very small circuit depths. Okay, but you can see it's not as small as you think, because each one of these thetas is actually this circuit here that involves 2 qubit and 1 qubit operations. So this really tells you, I mean, this is a variational type algorithm. This tells you more or less the state of the art for simulating things in quantum computers. But the reason I'm so excited is because you can see here, for example, the roadmap of IBM. IBM is thinking about this year releasing a 128 qubit device, then the next year 433, and the next year 1000. Will we achieve supremacy somewhere in between? Maybe. These are pictures of the chips that have simulated molecule over the years. James and I worked on this one back then, the 2010 hydrogen molecule experiment on a quantum optical table. Maybe Lorenzo remembers me talking about it already 11 years ago. But people don't even talk about this experiment anymore with Andrew White, because this has been advancing so far. This is actually the first experimental setup for the variational Eigensolver. We did the helium hydride molecule. I don't even talk about it again. So this is happening and happening and happening, and the chips become more and more professional. And then the question is, will there be an advantage? And I would argue yes. And with that, I'm going to end with this very, in some sense, happy, at the same time sad picture of my research group, because we were not in person, but we created a Zoom-like array of us. When there were low COVID numbers, we got together with our masks and took this group photo sequentially over a day. And so this is my group about a year ago. And anyway, on that note, I'm going to open up for questions. Thank you for your attention.
Thank you very much, Alán, for a wonderful talk. It's nice to see all the work put into context. As much stuff as you left out, right? It's a whole other 3 talks, right? So,
I mean, it's a colloquium, right, James? So I'm trying to present our work, and still it's technical. So sorry for those of you that were like, oh my God, this flew over my head. The best we can do.
Well, we have a question from the audience. One of our colleagues, former MIT faculty, Raul, will, let's see if we can add him to.
Raul, please bring it on. I mean, but by the way, you know, James knows my rule. The first student, Raul, you're a faculty, you said, right? But the first student that asks a question or postdoc gets $20 from me at the next APS or ACS. Of course,
you already got a postdoc question earlier.
Oh yeah, who was that person?
Joshua Heath.
Joshua. So Joshua, $20. So if you find me in an ACS, I'll give you Canadian or USD. If I have them in the wallet, if not, next time you see me, like eventually, I mean, I could be depleted by the time you see me, because I always do this in every talk. But Josh, you had $20 from me for asking the first question. So Rahul.
Yes. So, you know, if the largest simulation is 12 qubits, that's 1 part in 4,000. And if you look at the 53 qubit quantum supremacy processor, if you actually read the fine details of the paper, if it was perfectly quantum, a certain number would be 1. And if it was perfectly classical, a certain number, the cross entropy would be 0. And they actually achieved 2.2 times 10 to the minus 3. And if you look at the NISQ range that you have, the physical error rate needs to be between 10 to the minus 2 and 10 to the minus 3 for 30 to 300 qubits. And as you know, if you have more than 264 qubits, you have more atoms than in the universe if every single one of them were cross-coherent. So to me, the real figure of metric is not the number of qubits, which is nonsense. I can just take a whole bunch of qubits, but unless I can keep them all phase lock and coherent, which in chemistry should have to do with local interactions between fairly neighboring atoms, or maybe in the case of long-range transport with, you know, conjugate double bonds and stuff, longer. But that, to me, is the real question. Where will it get interesting in quantum chemistry when the number 2 to the n of the number of simultaneously cross-coherent phases in all of these states is good, so we can do something we could not do before?
I agree. And this might take 5 to 10 years. We don't know exactly when there is a breakthrough in the quantum control to be able to make this happen. I think it's in the hands of the engineers right now. People are talking about even the effects of cosmic radiation on the coherence and superconducting qubits. It's a very hot topic. So we might have these computers built, I don't know, in the bottom of the mountain or something like that, almost like a Jedi cave or something. So I would like to say that this is a very interesting era, because you're right, it's possible that we need to wait until the error-corrected machines to see this, or the NISQ computers will pull it off. And the reason I'm extremely optimistic is that I think in this room, Lorenza is the one that has been longest in the field. If she, I don't know, I'm going to ask this to Lorenza, but even me when I started in 2005, if I could never imagine that we would be so far away as we are today, with companies and IonQ going through a SPAC process of $2 billion and the incredible progress, I'm very optimistic that we will get to what you want, Rahul, faster than I even thought.
But Alán, I'm asking a separate question. I'm saying, in chemistry, where do you think that number n is? Is it 40? Is it 30? Is it 20? What do you think is actually the number of cross-coherent states that you need?
This you can estimate because
Yeah.
because there are people that do these tensor network calculations.
Yes, exactly.
And people that do these matrix product states, and which are related, obviously. And I would say that number to compete with a good tensor network calculation, as I said in the talk very briefly without more detail, is probably of the order of 100, I would say, give or take. There is a DARPA call that is happening, which, by the way, I'm actually applying to actually do this benchmarking efforts. And I believe it's going to be in the low 100 qubits, maybe 100, between 100 and 200. Because below that, because the metric is not all of them talking to each other. Chemical systems have locality into them, and they're banded, kind of, if you think about them in general terms. Like, not all the electrons talk to all them. So that all to all is not really true. So within that locality, people have been able to simulate systems that roughly correspond to 100 to 200 qubits. Somewhere around there. It just depends what you really mean. What is the benchmark? I can make a system that is more correlated than those systems that people were simulating with the MRG. I might need less qubits. So what I would say confidently to tell you that, I mean, to convince you, somebody that is more skeptical, I will probably have to get there to that level of qubits.
Are there any other questions from the audience? All right, so we have another one. This is,
well, we started with 1 or 2 qubits, so it's really great that we are at 12 right now.
so Jay Lawrence, is that who raised their hand? Does anyone else have a question? I saw someone raise their hand.
Anthony?
Anthony, perhaps?
No.
Maybe.
Anthony says no, he doesn't have questions.
I did not ask a question, but great talk. Thank you.
So Oscar Novak and Walter Lawrence have asked, and so we'll let Professor Lawrence see if we can. Where's our co-host? Okay, there we go. All right, you should be able to talk now.
Yes. Oh, thank you, James. So the question is, do you see a role for non-binary units?
Absolutely, Professor Lawrence or Walter. I don't know, James, to address you very formally.
Yes, Jay.
He's emeritus, so.
Okay, well, let me tell you something super, super cool. And actually, I think Lorenza will really like this paper. In collaboration with Alexei Galda at Argonne, my postdoc, a postdoc in my group that is just, she's amazing, Alba Cervera. If you guys are hiring, you should hire Alba, by the way.
Oh, yeah, Lierta.
Alba Cervera Lierta, which works in my lab.
She's working with Mario Kren.
She works with Mario and myself, and with Alexei Galda, they just did the first tripartite entangled state 000 plus 111 plus 222 on a quantum computer. Very little known about those states, okay? And now they're working on violating inequalities for them. But people usually think about multipartite entanglement in terms of qubits, but they access the second level of the IBM machines with quantum control, and they were able to actually create 3-qubit, 3-level entangled state. See, and then they did tomography, and you see the 0 plus 11 plus 22 state. And I really love that paper because it's so elegant.
Beautiful.
They did all that work, by the way. And the advisor that did very little on that, other than just clap at them and like, you know. Yeah, so that's Alba. Yeah.
I think we have time for one more question. And there's one more student, so let's see. Oscar Novak. I believe you have permission to speak, Oscar.
Can people hear me?
Yeah.
Awesome. So my question is, you were talking about having, let's say 100 qubits on a NISQ device. Well, making so benchmarking these errors could be quite expensive. So are there any efforts as to how to sort of push RB to a point where you can deal with such a large system without being having such a high cost?
You're talking about randomized benchmarking and technologies like that to actually figure out what is the error profile of the qubits, or what exactly you're worried about?
Yes. When you have a large amount of qubits, the cost for benchmarking these qubits can become, increased qubits can be very expensive. So if you have such a large NISQ device, how could you possibly figure out how noisy it is in a sense?
I don't think you will be able to do full benchmarking. You might be able to benchmark the modules, and you might be able to do what I just told you, eventually do a quantum computer simulator of those modules and then simulate their noise or the predicted noise and match the simulator to the real machine. I think there's going to be a moment where these devices will be like an experimental device. You build it and test it and see what happens, but you won't even be able to do all the necessary measurements to do this. I'm not an expert on error characterization, but if it scales badly, even if you have an approximate method that samples a lower number of operators, if it scales even with a low polynomial power, then eventually you won't be able to do it. You're right. And then this is where the young people have a job, right? Lower those exponents, like the students of Arthur and Arthur, right? So even what I like to say also historically, this is kind of a historical talk, is over the last 15 years I worked in this field, what really amazes me is the creativity of the collective mind of the world, the hive mind, on lowering these exponents and finding a creative trick. So maybe that's a good problem to work on. But I am not aware of specifics because I don't follow the field. It's likely that we cited some of the papers on that on our mega review, which obviously I participated on and worked and edited, but obviously I don't know all the hundreds of papers. That's why the paper has 15 authors, because we looked at different sections. So maybe check our review paper on NISQ, and there might be a section there on error estimation. Okay, I'm pretty sure there might be somebody thinking about that.
Okay.
Okay.
Makes sense. Thank you.
So with that, let us thank Alán virtually, as it were. On behalf of everyone else, we'll clap. Okay. And afterwards, we have a post-colloquium tea with you, Alán. I think you got the email invitation. If not, I'm sending around the meeting coordinates.
It says the password colloq.
Yeah, this is.
And there's the link, right? There's
Yeah,
the link.
I just put it in the chat.
Okay, I'll see you guys there.
Excellent.
Okay.
Okay, everyone. Thanks again, Alán. We really appreciate you coming to Dartmouth to tell us about the latest and greatest in quantum information science and technology. And we'll see you over at the tea.
See you at the tea.
Bye, everyone.